Cool. Yeah, so, alright, full screen, no mouse. Very nice, cool. So, name of the talk, you can read it, you have read it. My name is Arthur Tabatchnic. I work in two places. I work at Innoforce. We build medical software to help people. And I work at KeelDocs.io to make code documentation tools for developers. And in my spare time, a lot of the time I work on stuff that's concerning programming languages and compilers and different tools that help us to write in these languages. So, quick structure of my talk. I'll give a brief sentence about history. Then we will examine how a compiler works, what is the pipeline, how we get from code to an executable. Then I'll talk about the Roslyn compiler APIs, and then I will do some cool demos to showcase these APIs. I hope the demos are cool. So, a little history. Traditionally, a compiler is kind of a black box. It's a program, you install it, you give it a piece of code, it spits out an executable. Not very fun to hack around it. So, some time ago, roughly 2019, so 8 years ago, Microsoft decided to rewrite their C# compiler because everyone who was working on tools for C# and improving the workflow, they were writing their own software to parse the code and to understand it so that the programs can help you. So Microsoft decided to write an open platform. They called it the .NET Compiler Platform, a pretty boring name, so they nicknamed it Roslyn. It's named after a town in Washington by an ex-Microsoft engineer, I think, or something. So, Roslyn is an open compiler platform, as it says there, and we will now examine what that means, but first, we need to know how a compiler actually works, so we can know what possibilities it can give us as developers to do something with it. So, a compiler works in 3 steps. Not all compilers, at least the Roslyn compiler. It works in 3 steps. The first one is called parsing. It's where we take the code and we turn it into something more than just a text file. It's a model that has a lot of information. We'll dive into it a bit later. The next step is called binding. We have a model of what's happening in our code, but we as developers, we work in our .cs files and Visual Basic files. We want this knowledge that the compiler has. We want it bound to the files that we're working in, so our IDs, our tools, our editors can provide us with more things that we can use. And the last step is emitting, is where we take all of this information that the compiler has amassed from our code. It turns it into a DLL, an exe, or whatever you're doing. So, we'll examine all of these 3 steps in order. The first one is parsing. It is the biggest one, the most important one for our purposes at least. So, parsing itself contains 3 more steps. It is the first and the last time that there will be steps inside of steps, so don't be scared. We will examine these 3 steps in order. The first is called a tokenizer. So what a tokenizer does, it takes your code as text and it turns it into what are called tokens. There are different types of tokens. Let's say the reserved keywords in the language are a separate token, like words like namespace, class, var, and stuff like that. Then there are identifiers, which are the names that we give to things that we write, like name of a namespace, name of a class, name of a variable, all that kind of stuff. And then there is all the other stuff, which are usually some kind of text symbols. Those can be braces, brackets, commas, dots, all that kind of stuff. So the tokenizer, it opens your file, it reads it symbol by symbol, and it goes like, alright, I've read the word namespace and there's a space after it, so let me check if it's a reserved keyword in the C# language. It is cool, then it is a namespace keyword token. And so on, it turns the file into pretty much a very large array of things that we have written separated out. But it also contains all of the white space that we have, like new lines, tabs, spaces, all that kind of stuff, because we don't want to lose it. So let's say, the token of the keyword namespace. It also owns what is called a syntax trivia, and trivia is just all the stuff that isn't code, but it is around a token. So like comments, white space, if defs, compiler directives, all that kind of stuff. So we're done with tokenizing. Great. Next up, parsing. So a parser takes this pretty meaningless array of tokens and it gives it structure. It turns it into a tree. Pretty much all programming languages are turned from a stream of tokens into what's called an abstract syntax tree. We will just call it a syntax tree. A syntax tree contains only three different things, and those are syntax nodes, tokens, and trivia. So a node is something that contains children, so it's a node of a tree. Let's say a namespace, it contains stuff inside of it. So it is a node. A token is a leaf of a tree, so let's say the keyword namespace, it doesn't have anything inside of it. So it is a token, and trivia is everything else. There's white spaces, new lines, comments, all that stuff. What we will do now, we will take a look at a real syntax tree. So we've got a very simple class here, the same one that we had there, and in Visual Studio there is a built-in thing that's called a syntax visualizer. And if you open it up and click on something in your code, you get a tree. It's not very beautiful, so there is also a built-in visualizer for that. It looks a bit cooler. Oh, I already had it open, sorry. So let's close this ugly thing, open this marginally less ugly thing. So our code, it looks like this. It's a namespace and a class and some braces and nothing else. So, and this is the actual abstract syntax tree. At the root of a tree, we always have this compilation unit node. It means that it's just the root of a tree. It's either a file or a string or whatever you have. It doesn't really mean anything on its own. So we see that the root of our tree, it contains a namespace node and the end of file token. Inside of a namespace, we have an identifier name node, and identifier name is this thing, and we can see that before it we have a namespace token, which is the reserved keyword token in the C# language. And so you can see that all of this follows just the same structure. You have nodes and stuff inside of them, there are tokens, and trivia are just kind of like hanging around there. It's so that we do not lose our comments and white space when we use tools that use this tree. So we have our class declaration, and predictably consists of a class keyword, then our class name, and just a bunch of empty braces. Pretty simple, right? So back to slides. We're done with parsing. Fantastic. Now we have this hierarchical structure of tokens. It still really doesn't mean much. We can walk around it, we can like find the class, but let's say we want to know like, all right, is this class abstract or something? Okay, we can go and look for a token that says abstract. Let's say it has a property. We want to know, does it hide a property that it has inherited, or that kind of stuff. So the tree, it has all of the information kind of inside of it, but to get really all the information that we possibly can, we have to walk around the tree and find stuff and collect it. So the compiler does it for us. It's called symbol building. So what is a symbol? A symbol is a very smart object that represents a single thing in your code. Let's say a class, a namespace, anything in C#. So a bunch of symbols is called a semantic model, and it's kind of a knowledge base that a compiler makes about your code. So you can do stuff like, all right, I have this class from the syntax tree. I want to know a bunch of information about it. You ask the semantic model, like, what information is there? And it gives you everything. And symbols are very smart. They know let's say it's a class symbol. It knows if it's declared in your source text or in the dependency, in a DLL. They know which namespaces they're in. They know all the visibility modifiers, everything. They know their parents, their inside members and children, all kinds of things. So it's kind of the maximum amount of knowledge we can get using the Roslyn compiler. Great. We're done with the parsing step, but we're only done with the parsing step. But everything else is much simpler. So, binding. Right now we have built up this big semantic model that has a lot of information. It knows all kinds of things about our code, but we want to actually, it be helpful in our source code files. So we have to bind it back to our text, to the lines of code. So we take our semantic model, all of our symbols, and we have to find back where did they come from in the code in your project. So that is the binding step. The compiler takes care of it for us, no problem. So, so we're done with binding. What's left is emitting, which is just taking our code, the semantic model bound to our files, all of the information, and compiler will emit a DLL, a exe, whatever. What it does inside, it takes our syntax tree, it's a C# grammar syntax tree, and it turns it into a CIL syntax tree, which is the language that .NET runs on in the runtime. It's the common intermediary language of .NET, so everything, Visual Basic, C#, whatever else is turned into this format and then packaged as a DLL and shipped off, and you can use it. So, we are done with everything in a compiler pipeline, great. So, very boring, cool. Now what? Now, Roslyn APIs, as in the name of the talk. So, we've seen this pipeline, and the parsing step, it exposes a syntax tree API. The little visualizer in Visual Studio that we saw a few minutes back, it is written using this API, so we have access to this data structure. And also, it has the symbol API, because we have built up a syntax tree, and then we have walked this tree to gather all of the information, and we have a semantic model. So, via the symbol API, we can access the semantic model. Very cool. The binding step, after the binding step, we know where things live. We know from where to where the data flows. So, this is available in the form of a great API. Cool. And we have the emit API, which does exactly what you want. If you want to emit CIL from a syntax tree or something else, easy. So, very boring again. No, we can build stuff, but what kind of stuff? You know, it's a lot of APIs, but what can we do? You're probably already using a lot of tools built using these APIs in your everyday work, if you work with C# or Visual Basic or stuff like that. So, the syntax tree API, it's responsible for making your keywords different cool colors, like a class name is green, the word namespace is blue. So, that's done using the syntax tree API. If you want to outline your class, or you want to collapse something between two braces, you have to know where a thing starts and where a thing ends. Syntax tree API. All the automatic formatting, inserting spaces for you because you're too lazy, all those kind of things. Syntax tree API, fantastic. The symbol API is less used, obviously, in Visual Studio, but it does things like the object browser, or if you type Control comma and type in like the name of your class or search stuff, symbol API. Next up, this is what is used the most in Visual Studio and Visual Studio Code and all those kind of things. So you click F12, you want to automatically refactor something, you want to find where stuff is used. You click dot and there's a lot of IntelliSense happening. You're typing parameters in a constructor, it pops up and tells you what type is next and all the names and all the cool stuff that pretty much is impossible to work without, at least by now. So Binding and flow analysis API does it all. Very nice. Emit API. Not used a lot, but edit and continue. If you stop on a breakpoint, you type something in, you press a 5, it has magically somehow recompiled in the background. Emit API. But these are not all of the APIs. There's a Diagnostics API. All of the squiggles, errors, warnings, info, everything is implemented in the Diagnostic API. So let's say you have compiled a piece of code from your code and you want to run the regular Visual Studio like stuff on it, like find unused variables, find syntax errors, Diagnostic API. But let's say you want to do some harder stuff. Let's say you have come up with your own restriction. You don't want to have more than, let's say, 7 properties in a class because you're writing stuff for spaceships at NASA or something. So you want this restriction to work in your IDE when it's compiling on your CI machines, all that kind of stuff. You have to write it once, and you just plug it into the C# compiler, and it will run everywhere, so you can write your own custom errors, all that kind of stuff. It's very easy to do using the Diagnostic API. Oh, did I skip? Yeah, I did. So, scripting APIs. In the previous presentation, we saw LinkPad. And if you want to write something like LinkPad or a C# REPL, you can use a scripting API. It lets you execute pieces of C# code interactively on the fly, and it can remember what you have done before, so you have like this kind of living execution context, which is very nice. So let's say you want to embed like a little window for code in your product, and you want it to be C#, scripting API to the rescue. And last one is workspace APIs. Usually you're not working with like a single little file or a string of text. It's usually a large solution that has its configurations and dependencies and conditional dependencies and all that kind of stuff. So the workspace API abstracts it away, so you really don't have to think like, all right, this code is in this DLL and this and that, I have to put them together. It just blows it away and you don't have to think about it. It's just one big model that you can kind of wrangle. Let's build something already. Cool. We have heard a lot of words and seen nothing. So we'll have four little demos. The first is called syntax analysis. We have this basic piece of code, a namespace, a class, a method, and then one expression inside of the method. So what we will do, we will take this code as a string, we will turn it into a syntax tree dynamically via the C# API, and then we will poke around in it and see like what we can find there, what kind of information is available in there, what do the interfaces look like, and that kind of stuff. So let's go to Visual Studio. We don't need our tree. We will build kind of almost the same tree, except the code is a bit different. So we have the syntax analysis demo. So as a string, we have our code, the same as here. Nothing's changed. So the main thing here is the C# syntax tree class. You can use it right now if you want. You give it a piece of text, it gives out a syntax tree. Very easy, one line. And then, as we have seen, a tree in its root, it has the compilation unit. So we tell it, give us the first element. Really nice. So then we have this root, and we can go and dig around in it. Let's find out what kind of syntax node is it, how many members it has, how many usings it has. Cool. And we can also, these usings are just a list of a using node, so we can go inside of it and type out all of the usings that we have in our code. So deeper, the first member of our root is the namespace declaration. We can get it, we can verify what kind it is. Inside of the namespace declaration, we have our class. We go deeper. We go into our namespace. We take the first member. we'll do the same things. We see how many members it has, what kind they are, and we will go even deeper inside of the main method. So, and about a method is a bit more interesting because it has more things in it. It has a return type, it has parameters, it has a whole bunch of different things. So we can see what is the return type of the declaration of the main method. Very easy. We can see how many methods it has, how many parameters it has, and if we call to full string, we can even see the full code text of this method. It's pretty simple. And right now we are kind of digging manually inside of it. We're taking the 0th element of something, going in, once again, the 0th element. Not that dynamic if you think about it. So there is also, of course, a link API. So these 4 lines, they do everything we have done above. So we take the root, we see what members it has. We want to find the method declaration, which is the declaration of our main method. We can do it with regular link stuff. And then we want to find, let's say, the one that's called main. In our case, we have only one, but still it returns a list, so we have to somehow filter it. And then we want to take the first parameter of this method, and we can compare. This is the parameter that we have found manually, and this is the parameter that we have found via LinkU. And we will compare if they are actually one and the same. So we can run it and see what it tells us about our little piece of code. So let's open up our little piece of code here. So we have it. The text is quite small, but I hope you can see it. So it tells us that indeed the root element of the tree is a compilation unit node, as we saw in the visualizer. It has 1 element in it and 4 usings. We scroll a bit up here, direction 4, it's not aligned. Next, the first member of the compilation unit is a namespace declaration. That's correct. It has 1 member inside of it, a class declaration. Cool. Inside of it, there's a 1 method declaration. Correct. And then we can see all of the information that we read about the main method, the return type, how many parameters it has, the type of the first parameter, and the full text. And now we are comparing the stuff that we found using LinkU and using manually, and we can see it is indeed correct. So, while this is cool, it's not that super obviously useful, but in this first demo, we have taken a piece of C# code as a string, we have turned it into a syntax tree, we have poked around in it, we have queried it, we have found stuff in it manually, all kinds of cool things. Next demo is the semantic analysis, and if you remember, the semantic model is when we walk around the syntax tree, we gather all of the information that we can, and we have kind of the smart knowledge database about our program. So, semantic analysis. Let's go into here. So, the same piece of code as a string as we had before. Nothing has changed. Same thing as before, we turn our text into a syntax tree. We get the root node of it to play around with it. But now, we want to actually create a semantic model. For that, we need to create a compile. What is called a compilation, it's not compiled code, it's called a compilation. We create it, it's just 1 line, and then we can ask the compilation for a semantic model. What we have done here, in this demo, we will play around a little bit with the type string, and for the semantic model to know stuff about the type string, we have to give it the DLL where the string lives, or the source file, which we are doing exactly here. So right now, our semantic model, it has the information about our little hard-coded piece of code and the type string. It doesn't matter that the string is not a source file, it's a DLL, it's totally fine. So we have gotten the semantic model, and now we can go into the syntax tree, find a node, and ask the semantic model, like, what's the information about this node? Like, what have you found? So we are going into usings. We're taking the first one. I think it's using system. Yes, it's system. And we are taking its name, and we are going to this semantic model and telling us, hey, I have the symbol system name. What do you know about it? And it gives us back symbol info, and it has a lot of stuff inside of it. We will only take a little bit of it. A symbol knows about in which namespace it lives and who lives in the same namespace with it. Because the semantic model, it builds up information about all the parents, all the children of everything. So we can take the information from our, oh sorry, my touchpad is very bad. So we can take that information and we can just straight up ask, tell me what's in the same namespace as myself. And we will just output that. We will see that in a second. Now, we want to find something more interesting, and we will find our string. So we want to find a little piece in the tree that is this string literal, our hard-coded hello world string. Oh, too far. So we're doing that using LinkU as we did in the previous demo. We're going to the root, we are taking all the members, we're taking give me the first literal expression syntax. Well, it's the only, so that's why it's using single. A literal expression syntax is a hard-coded value, it's an integer, it's a string, it's something that you have hard-coded inside. We are finding it, it's our hello world string. And once again, we are taking this piece of syntax, we're going to the semantic model and telling it, hey, like, what do you know about this thing? So it gives us back the information it knows. And let's say we want to find, the type string has a lot of methods in it. Let's say we want to find all of the ones that are public and that return another string. So these are methods that just kind of modify the existing string and return us a new one, or like maybe it's a static method that generates a string or something. So, easy. We have all of the information from the semantic model. We tell the API to give us all of the members inside of it. Then we want to filter them to only be methods. Easy. And then we filter them to a return type of string and accessibility of public. If someone has used reflection, it's kind of similar, but Roslyn APIs are like reflection on insane steroids kind of. So, and all of this, very large, very annoying. So once again, we can do the same stuff using LinkU. So, you know, it does the same things, and we will make sure it's so. We found all of the methods on the type string that are public, and then return another string, and we will just output their names to the console. Oh wait, no, I ran into the wrong thing. Sorry. I have the semantic analysis. The habit to flick F5 is a bit too strong. So, as we saw before, we found the first using in the program, which is system, and we have found everything that lives in the same namespace, which apparently is just a bunch of other namespaces, which is not a surprise. So, and next up, we have taken the string literal, we have found its type, we went inside of it, we found all the methods on it that are public, that return another string. So these are all of the non-extension methods that are defined inside of the type string. So, back to our slides for a second. we have taken a piece of code, same as before, we have turned it into a syntax tree. Then we have walked this tree and gathered all of the possible information. And then we have queried the semantic model for information about both the code that we wrote ourselves and the stuff that people at Microsoft have written for us. Next demo. Up until now, we have only read code and read information about this code. But we want, let's say, to build tools that refactor stuff for us, that detect something. So we want to actually modify existing code. So in this example, it's a very simple example. We will take the second using, which is system collections, and we will turn it into a system collections generic. Very simple, but it will illustrate a lot of useful concepts. So syntax transformation demo 1. So, same as before, we have our hard-coded code. So, our workflow here is we want to take a syntax tree, we want to find the node that we want to replace, then we want to create a new node, we want to swap them out and save this new tree as a piece of code. Very simple. So, what we will do first, actually, we will create the syntax node from scratch. For that, there is what's called a syntax factory. It's set up as using static because otherwise it's very, very long. So if you see something that doesn't seem right, it means that it's probably in the syntax factory static class, but that just gets very long and cumbersome. So we want to change the name of a namespace that we are importing. That's called an identifier. Everything that is a name of something is an identifier. So usings are no exception. So first we are creating a new identifier, which is with the value of system. But it has dots after it, so we need to add that on. In C# stuff with dots after it is called a qualified name. So we're telling it, all right, we have a name, we want to have a qualified name that starts with the previous name and adds on collections, and the same with generic. So we have built up from scratch a node for the syntax tree that is absolutely valid and that has the information that we want. So now we need to find where to put this node. So same as before, take our stuff, turn it into a syntax tree. Now we want to find the using node. We know it's the second using in root. So easy enough, root, the second using. And we can just take our existing node and plug it in. But in the existing code, the using node has some extra stuff. It has trivia. Maybe it has comments on top of it. Maybe it has an attribute on top of it. Maybe it has like comments on the same line or 10 new lines after it. We don't want to lose this information after we have updated the syntax tree. So what we can do, we can take the old using and every single type in the syntax tree has a bunch of methods that are called with and something, and what they do, they give us the same node, but with the updated something. And since everything in the Roslyn API, the syntax tree and stuff, everything is immutable, it's made for performance and thread safety if a lot of tools are running at the same time. So this is the way how we get the old using. We replace only the name and we leave everything else intact. And then a syntax tree just has a method replace node, old node, new node, done. So let's run this. Let me not click by accident this time. very fast. So first we're building up our qualified name system.collections.generic. So first off we have system collections, generic. This is our old code, and this string is not the initial string, it's what the syntax tree gives us back. And after we run all of our operations, we can see that the second using is indeed updated. And now we can compile this syntax tree into DLL, we can create a semantic model, we can do all kinds of things, and it is updated. We have not lost like any white space after it, the new line still exists. So this is a very basic way to update a piece of code using the Roslyn API. So we have created a new syntax node from scratch. We have found the target and we have replaced it. Well, we haven't actually replaced it. We have created a new tree with that node there, because trees are immutable, but for us it really doesn't matter. So, and the last demo, we want to do something fancier. We don't want to find stuff manually. We want we want for it to happen automatically in like a whole file, like a whole project. So, what we will do, we will take a little bit more complicated piece of code, and we will replace all of the explicit type declarations to an implicit one. So if there is something like the example, on the left there is a type, on the right there is exactly one thing, we are initializing only one variable at a time. There is a definite type on the right side, and the type on the right side is matching the type on the left side. We know that if we replace the type on the left side with var, we are not losing any semantics, it will not crash, it's safe to do. So, last, biggest demo, super scary. So, in the previous one we have done everything manually, but we don't really like that. So there is a thing called a C# syntax rewriter. It is a thing that helps us transform a syntax tree. What it does, it is a class, it takes in a syntax tree and it will visit every single node of this tree, and at every single point it will give you a choice, either to replace it by a new one, to delete it, to add some more ones, or just not touch it. So, what we want to do, we only want to actually touch the declarations of variables, which in C# grammar are called local declaration statements. So a rewriter has like, I don't know, maybe like 200 methods that you can override, one for every single type that you can possibly find in the tree. So we are overriding only the local declaration statement method. It gives us the node from the tree that we are visiting, and all we can do, we can return another node. If we don't want to change anything, we just return the same node. If we want to change it to a different one, we return a different node that we have built up from scratch or created using the existing one. So, since we are not handling the cases, or we are initializing more than one variable, we skip this case. We return the node as is. And if the initializer is not present, so someone has written my type, my variable, semicolon, we can't replace it with var because we don't know the type. It's not valid C#. So that we are also skipping. First, we need to see what type we're actually declaring. So, very easy, we have the node, we know it's a declaration node. So if we press dot, it pops up declaration. In the declaration, there can be multiple variables. We just need to make sure there are, and we take the first one. And we want to find which type it is. Node, declaration, type, easy. Then we want to find what's on the right side, because we need to compare these two things. Also easy. For this, we will be using the semantic model and just get the info about this assignment. Yeah, some more boilerplate stuff. And if these types match, we can safely take the token on the left side, that is the type name, we can throw it out and we can put in var. Very cool. So, using the C# syntax factory, we are once again creating an identifier, name of var. But if before we have used the with name method to copy the node and replace the name, here we are actually changing the type of the node because my type and var are actually two different things in the compiler. But we still want to keep all the trivia, all the comments, attributes, and white space and stuff pretty easy. We take the old one, we get the leading and trailing trivia. It's the stuff that is in front and after an element, a syntax node, and we use the appropriate methods to paste it on. And then we go into our node that has been passed in. A node that is passed in is like a miniature tree, because as we know, nodes contain stuff inside of them. So we can use the same stuff as we use for the root of the tree, which is the replace node method, and we give it the old one, we give it the new one, and it's replaced by our new node. And if the types were not matching, well, let's say on the left side there is a base class, on the right side there is an inherited class, the semantics will be lost if we replace it with var, so we just don't touch it. So now we have this syntax rewriter, but we need to somehow apply it to our piece of code. And the piece of code we will be applying it to is this code itself. So it's kind of a self-modifying code. Not really, but you know, it sounds cool. So in the main method, we have a test compilation, which is the same stuff we've been doing before, except we're reading from files. We're taking this file, we're taking the syntax rewriter file, we're reading the text, we're creating two trees from it. We are getting all the metadata about them, just in case if you know there are some dependencies and stuff, we don't want to miss them. And we are creating a compilation, the same as before, which is the semantic model. Well, it contains the semantic model. So we have created a compilation. It will contain two syntax trees, one for each file. We will just enumerate them, get the semantic model, then we will instantiate a new syntax rewriter using this model, so it knows like the information that we have given in the dependencies and whatnot. And then the rewriter just has one method, visit. You give it the root of your tree. It goes into all of the possible places in the tree. It checks if we want to do something with this type of a node inside of the rewriter. If yes, it applies it. It replaces or doesn't replace the node and goes out. So yeah, if something has changed, we just take the syntax tree that we have instantiated as a string and we just dump it back into its text file. So let's take one last look. There's a bunch of explicit stuff, and let's see here on the left we have type syntax, and on the right we have identifier name syntax. So while it will actually compile, if we replace it with var, we are losing some of the semantics. So this one will stay put. And let's run it and hope that nothing explodes. probably. So it's running, it's doing all the stuff. So, and Visual Studio tells us that code has been modified. We reload the file, and we see that all that stuff has turned to vars, and this thing has stayed put. Very nice. So we have done a whole lot of stuff. We have read the code from CS files. We have learned to use the syntax rewriter. So we dynamically walked the whole tree, identified the target nodes. We modified them and replaced them in the tree. And we have taken all of this stuff and we have put it back into our source files. And if we see, let's say, this one was replaced by var. On the top of it, there is a comment, and in the syntax tree, comment is owned by the next token. So nothing is lost, all the white space is the same, all the tabs are the same, all the comments, all that kind of good stuff. So, very nice. And I like complete workflows, so quickly you have written a tool using these APIs. Of course, you can package it as a Visual Studio extension or as a VS Code extension, but the year is 2019, we have .NET Core and everything is cross-platform. So a cool thing that I like are .NET global tools, and if you have written your tool, it's super fast to package it and publish it. You open up your CS project file, and you add pack as tool, tool command name, and the output path, which actually is optional. So this is my new awesome tool. Then I just call .NET pack, and I can install my tool. I can install it on my machine. I can give it to my colleagues. I can put it into a NuGet feed and use it as a NuGet package. Very nice and very useful. And .NET tools, they work on all platforms, same as the Roslyn APIs. They work on the .NET standard, usually the latest one. So all this stuff, starting from the year of 2014, is not bound to Windows anymore. You can do it on Linux, on Mac OS, or whatever target that you desire. So that, I think, is pretty exciting. So, does anyone have questions? If you want to play around with the demos, you can go to my GitHub. I'll also put the slides there. I don't think I put the latest version there yet, but I will do it after the talk. So, yeah, and if you want to comment on how bad my code is, you can open an issue in GitHub and scream at me. Very nice. Does anyone have any questions? Yes?
Yeah, very nice presentation, thanks. I'm so curious about, did you get any chance to use it like really in production?
I mean,
other than just playing around on your own machine with your development environment?
No, I mean, this kind of stuff in production with these APIs is kind of making a widely used tool or something? Or
kind of. Can you come up with any other idea rather than just creating a next resharp or something like that?
Yeah, sure. Let's say the built-in static analysis in Visual Studio is pretty basic, pretty simple. You can apply all of the latest academic papers on static analysis and data flows, and you need to use these APIs. Or let's say you want to, I don't know, you want to transpile from C# to something else. You want to transform the syntax tree from something to something. Those kinds of things would be definitely possible.
Right.
Or let's say you want to, I don't know, you have your other like piece of software and you want to embed like something scriptable with C# and you want to receive the code, you want to format it, you want to check it for errors and all those kind of stuff. Or let's say you want to write optimizations. Like automatically you have your syntax tree and the semantic model, and you have your new crazy method where you have calculated that if you take these types of nodes in this format and you can transform them, it's guaranteed faster.
And are you currently working at your work? Are you currently using some tool created on the base of Roslyn?
I mean, all of Visual Studio tools are created based on Roslyn. All of the extensions in Visual Studio are created.
Yeah, I mean,
using Roslyn.
that you have created.
No, right now.
Okay.
I don't have, sadly, that much time to go write my tools.
Alright.
It would be very fun with jobs for writing these kind of things.
So it's not really applicable in your job situation, but it's just for playing in your spare time, right?
Right now, yes.
Okay.
I mean, if I'll find a case where I can write a tool and it will help me, sure.
So, yeah, this is what I was interested in. Thanks.
Yeah.
Cool.
Other questions? All right, then, thank you for your attention. Visit my